technically, if you think about it, you can have an algorithm that uses your glucose monitoring data or your glucose data that CGM is reading, and then we can figure out if the patient is at risk of cognitive decline or not. And it seems like the algorithm can distinguish between a patient that is having issues with cognitive decline and the patient who isn't. We started with fully supervised machine learning algorithms. When we were doing this, we were testing different algorithms. And one of the algorithms' job was to push the prediction horizon as far out as possible. So we set it off and we noticed the algorithm was doing a really good job of predicting future events. So like, oh, that's kind of interesting. The issue is with deep learning models and fully unsupervised techniques, you can't really tell what's happening inside the algorithm. Where is it learning? Where's the data accumulating? So we had a project where the government subsidized our resources to create a visualization matrix to be able to see what's happening inside the algorithm. What we noticed was that the algorithm was actually sectioning people into different subgroups. And this was interesting because when we look at somebody's data, you really don't see subtle differences. But to the algorithm, there were subtle differences between the data that we were feeding it. And for us, it was like type 1 and type 2. That was the only difference in terms of the data that we were feeding the algorithm. But the algorithm was able to subsection them and stratify them into different sections and different clusters, as we refer to them. So to us, that was a little bit of a, like, what is going on here? Back then, we didn't have an integration into electronic medical record, health record system. So we ran an internal study asking the users, have they been recently diagnosed with something? Have they been taking a new drug? Like, what is triggering this difference of clustering? And we had high correlation of cognitive decline, different types of cognitive decline. The strongest one was Alzheimer's disease. So I was like, okay, we started with diabetes. What does that have to do with cognitive decline? So I went back and checked the research. Back then, they just discovered that the amyloid protein that builds up in the brain and solidifies is quite rich in glucose. So in fact, when they did the PET scan for patients that had Alzheimer's disease, they often inject them with a nuclear dye, and that dye essentially binds to glucose. And then they realize that they're getting like these amazing scans of the tau protein that's causing the Alzheimer's disease. And then the hypothesis that actually came to light, and that's something that we're investigating, is that there seems to be an alteration in how glucose is metabolized. And considering that your brain consumes about 25% of your entire daily sugar intake, glucose goes into the brain, it doesn't get processed the way it should be, creates a byproduct that we refer to as that solidified tau protein. If it solidifies where it's not supposed to, it essentially covers your neurons and starves them effectively. So glucose goes in, byproduct gets created, it solidifies there, and oftentimes your brain is kind of surrounded by this blood-brain barrier. It acts as a two-way filter. That's why people don't get brain infections and other things, right? Because it helps protect the brain against viruses and bacteria, and there are no immune cells present within the brain. So goes in, gets created, sits there, and over time we know this as Alzheimer's disease. So that's when kind of like a light bulb went off in my brain and kind of just like, oh, this is interesting. So technically, if you think about it, you can have an algorithm that uses your glucose monitoring data or your glucose data that CGM is reading, and then we can figure out if the patient is at risk of cognitive decline or not. And it seems like the algorithm can distinguish between a patient that is having issues with cognitive decline and the patient who isn't. So then I started reading more into it, and then I realized that we have a lot of patients with prediabetes. Of the patients that we put on the prediabetes label on, only 10% of them develop diabetes. And that's not because our medical system is so good that we're preventing the sort of progression of the disease. It's the fact that they developed prediabetes and then they developed a chronic condition that's far more severe that dwarfs their entire diabetes progress. So it's in fact killing them faster. So then we really doubled down on the clustering project. So I think there will be a day where we can put a continuous glucose monitoring on someone, and we'll be able to monitor how their body's reacting. Are they aging faster than they should? Are they having an issue with an asymptomatic disease that hasn't shown symptoms yet? It's almost like, Today, we have less cars broken down street corners because, since the 1980s, we started putting engine managers in, and our bodies are very similar to our cars, right? They're just like this metabolic machine, right? They burn glucose instead of gas, right? So I think continuous glucose monitoring is really exciting because it allows us to monitor the inputs and outputs of the engine, and your body being the engine here. And we can easily figure out when something goes, not the way it's supposed to. And it's easy to understand. But unfortunately, diabetes has really skewed our understanding of glucose metabolism and prediabetes. One of the things that we're working towards is splitting the prediabetes group into different groups and people with different types of glucose behavior based on their glucose phenotypes. And that allows us to better predict diseases. So for diabetes, yes, we're doing, there's a need there and we want to address it. But potentially being able to monitor glucose fluctuations, not as a monitoring tool, but as a diagnostic tool, I think is huge.